Hi everyone, my name is Yujie. Today I'm introducing our work that changes users' perceived softness when touching a real rigid object. This work is done in collaboration with Shan-Yuan Teng and our advisor Professor Pedro Lopez at the University of Chicago. Here I'm asking a user to touch two objects and tell me which one feels softer. Because human perception of softness is so good, which we heavily leverage every day when manipulating different objects, this user easily identified that the blue object on the left is softer than the beige object on the right, which is totally correct. Now, I'm asking the user to touch the two objects again and answer which one feels softer. This time, we actuate the device before the user touches the beige object. Look, with this actuation, the user sets the beige object, which is naturally rigid, as the softer one. What I'm going to present today is this wearable device that enables a rigid object like a wooden chopstick to feel as soft as a pencil eraser. Our device works by modulating the contact area between the object surface and the finger pad, which prior work have validated as a determining factor for human perception of softness. To better explain how our device achieves contact area modulation, let's compare touching a rigid object with bare finger pad, touching a soft object with bare finger pad, and touching a rigid object with our device. When touching a rigid object with bare finger pad, as the object is rigid, it doesn't conform, which leads to a small contact area between the object surface and the finger pad. When touching a soft object with bare finger pad, the object conforms to the shape of the finger pad, which leads to a larger contact area. Now, let's see what happens to the contact area when the users wear our device and touch a rigid object. At first, our device is not actuated and the finger pad is in its normal shape. And now, we pull the hollow frame onto the finger pad using a motor. This restricts finger pad's lateral deformation and makes it bulgier. The restriction on lateral deformation leads to a larger contact area between the object and the finger pad, which is similar to touching a soft object. If we release the pull of the motor, the finger pad resumes to its original shape. This time, the contact area is similar to touching a rigid object. We conducted two user studies to validate the softness illusion induced by our device and its usage in different applications. In the first study, we performed a staircase experiment to identify to which level our device brings down the perceived softness. We provided participants with rubber stimuli of a range of softness. Specifically, our test stimuli include objects ranging from 40 short A to 90 short A. To give our audiences more context, a pencil eraser is around 40 short A and a skateboard wheel is around 90 short A. Our result shows that our device is able to bring down the perceived softness of any object between 50 to 90 short A to around 40 short A. As we have validated our device can induce softness illusion, we want to show how it works in different interactive applications, where our users are not blindfolded and can directly see the device. We have our participants to try out two applications. The first one is a VR application where we use wooden chopstick as props for pencil erasers. With our device, the users are able to feel one eraser is softer than another. However, the props are exactly the same. In the second application, we asked the user to play a video game with a 3D printed rigid gamepad. With our device, the users would feel the button as soft. We found out that compared to bare finger pad, our haptic device provided more realistic haptic feedback, and it was the preferred interface by our participants in both applications. As of this point, we will introduce how our haptic device alters perceived softness of real rigid objects by restricting finger pad deformation. What I haven't talked about is why we built this device. To uncover the motivation of this work, let's rewind how prior work induces softness sensations. To simulate softness experience, one approach is to attach actuators directly to our body. Prior work has leveraged techniques such as stretching fabric banks, vibrotactile actuators, and shape memory alloy. Those techniques are great. However, with those devices, users cannot feel the texture of real objects. The applications of those devices are limited to simulating virtual objects. Another approach researchers have tried out is to instrument the object themselves. We have seen prior work using visual or audio cues or adding haptic actuators directly to the objects. While those instrumentation provide softness alteration to everyday objects, to achieve ubiquitous interactivity, it requires to instrument every object the users might in contact with, which is not always feasible. Instead, our wearable device alters the perceived softness of real rigid objects. It works without object-side instrumentation, and our design goal is to leave most of the finger pad free. To better understand the engineering of our device, let me walk through the components that implement our wearable device. Our device contains a holoframe which serves to restrict the finger pad deformation, a DC motor that pulls the holoframe, a pulley system that winds the pulling string, a force sensor whose value is fed into our control loop, in which case it's a simple PID, to control the pulling force. Our custom PCB also contains an NRF chip with Bluetooth Low Energy module, which enables our device to communicate with various applications in VR and AR environment. The applications of our device are also beyond what we have covered so far. In our user studies, we validated our device can enable the same VR props to display different softness states. More applications of our device include rendering soft button experience to everyday objects. For example, here we have a 3D printed phone case with the little protrusion on top. You can see it is tracked by capacitive sensing. More importantly, when the user touches the rigid protrusion with our device, the user feels the protrusion as soft as a rubber button. Moreover, our device can also enable changing material softness without reprototyping. For example, this teddy bear is 3D printed and completely rigid. With our actual device worn on hand, the designer can test how does it feel like if the hard part of the teddy bear is printed in a softer material. Today, we introduce you to this wearable device that alters perceived softness of real rigid objects by restricting finger pad deformation. This work aligned with prior projects from a lab at Chicago, such as Magnet.io and Touch and Fold, which also strive to achieve tactile feedback while keeping the finger pad free. We believe this is an important new direction for haptics, in which we urge the community to create haptic devices not only for feeling virtual environments, but also play well in haptic innate to our real-world experience. Our vision for this project is to push forward haptic devices that work across interactive regimes. This allows users to move fluidly from virtual reality to augmented reality without having to take out their devices. Thanks for your interest in our work. You can find our open source software and hardware design files in the link at the bottom of the page.